Hey guys, what's up? All right, so binomial theorem. We are pretty much cutting out chapter 12 thanks to our friend COVID-19. Me and Miss Carp agreed that you've seen it in Algebra 1 and Algebra 2. And the only thing we need to relearn in this year is the binomial theorem, because you did not see that in Algebra 1. The rest of the stuff you've seen twice and is not a huge thing in future courses. So this 12.5 is the only section we're going to cover from chapter 12, and it is going to be on the chapter 11 test. So we're just mushing it in because it's only one section. It doesn't make sense to make its own quiz or anything for that. So the binomial theorem. Okay, so we'll fill this blank in eventually. That's actually not going to be the first thing that we're going to do. We'll fill it in eventually. But I want you to expand these. And I actually want you to multiply out x plus a times x plus a times x plus a times x plus a for this, even if you remember the binomial theorem, which I would be really happily surprised if you remember the binomial theorem. So pause me and take a minute to multiply. Obviously, this to the first power is just that, right? And then FOIL that out, and then multiply that out, and then multiply that out. All right, so we all know this one, right? Is that. And then we know now we're doing to the third power, so that's the first power times the second power, right? So just multiplying these two together to get that one. And then we're going to do a bunch of distributing. So first times first, and then keep distributing. I'm not going to have space, am I? And then distributing the a. Let me see. Ax squared, right? Distributing the a. And then the last times the very last. I should have left myself some more space. I'm going to have to go up. Sorry, that's a little bit messier than I usually like to go. So the x to the third doesn't have anything to combine with, but I have 2ax squared and 2ax squared. Oh, I combined the wrong things, didn't I? That's not right. I have 2ax squared and ax squared. Be careful right there. Don't do what I just did. That should be 3, yeah? And I'll tell you how I knew I made that mistake when we get down to Pascal's triangle. So I did that. Now I have a squared x and a squared x. So that should be 3. And then just the plain old a cubed. And then to do something to the fourth power, we can do squared squared, right? And I'm really going to run out of space on this one because it's going to be even longer. First times first, I'm going to try and write small. And then distributing. And keep distributing. And keep distributing. I'm going to line things up if I can. So this term is going to be a 2ax cubed. So I'm going to put it under the 2ax cubed. And then this term is going to be what? A 4a squared x squared. And then this is going to be a 2a cubed x, which I don't have yet. And then distributing here, I've got another a squared x squared. And I've got another a cubed x, 2 of them. And I've got an a to the 4th. So combining those like terms. Oops. What is that, 6 and 4 and then a to the 4th. So first I want you to just recognize some patterns that are going on with the variables x and a. Usually when we're talking about expanding binomials, that a is going to be a number, right? We're used to seeing like x plus 1, x minus 7, or even 2x minus 3. Let's focus on the variables first, and then we'll talk about the coefficients down here. So notice that the degree of each term, remember terms are things that are separated by addition or subtraction, the degree of each term matches the degree of the original thing. This has a 1 and a 1, that degree is 2, that has degree 2, that has degree 2. These are both degree 1, right? And I can keep going. This is degree 3. This has a 1 and a 2, so that's degree 3. This has a 2 and a 1, so that's degree 3, and so on and so forth. And you can do the same thing down here with the fourth powers. That's a 4th degree. That's a 1 and a 3. That makes 4. That's a 2 and a 2. That makes 4, and so on and so forth. So that's the first check for when you're expanding binomial theorem problems. Also, notice that the first term of the binomial starts at the highest power in the expanded form and decreases. So this goes 2, 1, 0. This goes 4, 3, 2, 1, 0, right? This goes x to the third, x squared, x to the first, x to the 0, okay? The second term in the binomial starts with nothing and increases. So this is a to the 0, a to the first, a to the second, a to the third, a to the fourth. Okay, so we're going to note that it's x to the n plus x to the n minus 1. I'm going to leave a little bit of space for the a. X to the n minus 2. I don't think I'm going to have space. Let's see if I can squeeze it in. And then all the way down to something with a plain old x. And then, oops, I didn't leave space for the coefficient. And then something with no x. Okay. And then the a starts with nothing, a to the 0. Whoops. And then a to the first, a to the second, a to the, oops. What did I just do here? That should have been a 2. I said n minus 1, n minus 2. And then this is going to be the dot, 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 right? So this is the, I got carried away. This is the a to the n at the very end, just like the very beginning was x to the n. So this is going to be a to the n minus 1. And you can check it, just like we discussed. The sum of the exponents, which is the degree of the term, should equal that. N minus 1 plus 1 equals n. N minus 2 plus 2 equals n. 1 plus n minus 1 equals n, and so on. So now we just have to figure out the coefficients of each of these. This one I didn't leave space for. We have to figure out the coefficients of each of these. So here we had a 1 and a 1. Here we had a 1, a 2, and a 1. Here, where's this one? Here we had a 1, a 3, and a 1, and so on and so forth. 1, 4, 6, 4, 1. Okay. We can use combinations to get the coefficients. This is the formula, and we'll use it in a second. The j is the second. Let's write a note about this. This is the exponent on the x, and this is the exponent on the a. Okay. Fact to remember about factorials. Oh, that was kind of funny. Haha. Fact about factorials. Okay, this video is going to be a little bit longer than usual. I apologize, but there's a lot going on here. 0 factorial is equal to 1. It's a definition. Just trust. Okay. Pascal's triangle. I prefer to use Pascal's triangle when I'm doing the coefficients. So these are two different ways of doing the same thing. You might remember that Pascal's triangle has 1s going all the way down. And then once you get to where you can add two things together, right? So add the two things that are above it, and then 1's going all the way down. So I can add these together, and I can add these together, and I can add these together, and these, and so on, and so forth. And you can see, so the thing that you have to remember about Pascal's triangle is this top row represents x to the x plus a to the 0 power. It starts with the 0th power. Anything to the 0 power is 1. This represents x to the plus a to the first, the coefficients. And if you look here, x plus a to the first, the coefficients were 1 and 1, and that's what that's telling you right there. And then x plus a, I'm not going to write all of these out, you'll get the gist of it. X plus a to the second, this tells me the coefficients are 1, 2, 1. And if I look at the work that we just did, the coefficients are 1, 2, 1. Third power, 1, 3, 3, 1, 1, 3, 3, 1, and so on. And that's how I knew I had made a mistake on that, because when you've done this enough times, you recognize or remember the first many rows. So the only place that people sometimes make mistakes on Pascal's triangle is forgetting that that top row is the 0th power. But if you think about it, this only gives me one coefficient. If I'm trying to apply it to the first power, I need 2 coefficients. So I need to go to the row that has 2 coefficients. All right, so this is a general form for the binomial theorem, including the coefficients. You can see that, just like I said up here, the exponent on the a matches this bottom number here. And sorry, this is wrong. This is not right. This is the exponent on the original binomial. Sorry about that. This is the exponent on the x. So it's original exponent divided by each of the exponents of the term. This is really abstract right now. It will come together when we do the example in about 10 seconds. Okay, so the exponent on the a here, there is no a, so that's 0. The exponent on the a is j. The exponent on the a is n. The top of that notation for a combination is always the original exponent. Let me do that in a different color. So this goes here always, and this goes here. Okay. And there's combinations on your calculator. I'll show you that also. Okay, so let's do an example. Hopefully you guys are pausing me to write this stuff down as you need to. All right, so we're going to expand using the binomial theorem. The first term is 2y, and the second term is -3. So I'm going to start by saying, okay, the pattern that we recognized was first term starts out at the highest power, and it decreases. I never give myself enough space here, and then sometimes I give myself too much space. Second term, -3, right? Because the binomial theorem has a plus in between, so this is plus -3. Starts with nothing, and then it increases. So first power, second power, third power, fourth power. Okay? I could very easily, so those are my terms, I could very easily use Pascal's triangle here. The fourth, so 0, 1, 2, 3, 4, 1, 4, 6, 4, 1. But I want to show you how to do this using the combinations. So you might notice that these are always 1. The coefficients here before you expand are always 1. I'll show you remember we're using this notation, and then we'll talk about what that notation means in a second. Original from the binomial, see, I'm not giving myself enough space, goes on top, always, of that combination notation. The exponent on the a, or the second term, goes on bottom. There is no -3 here. This is a first power, this is a second power, this is a third power, and this is a fourth power. So that's my expansion, and now I just have to figure all of these out. So how do I evaluate 4, choose 0? That's how we say that. 4, choose 0. Well, we're going to look here. The n and the j, so 4 and 0. So I'm going to go n on top, n factorial, over j factorial, n minus j factorial. Okay, I'm going to do the same thing. N on top, 4, j factorial, n minus j factorial. And I'm going to keep doing that. And on top, j and minus j. And what you might notice is, hopefully, the denominator matches these exponents. So the numerator is always the original, the denominator matches those exponents, so you don't really have to think about it as much. So I'm going to go numerator and then 1, 3. The order doesn't matter, right? Because those are being multiplied together. Okay, and then numerator and 4, 0, because there is no 2y term. Okay, this marker is kind of obscenely loud, isn't it? All right, and then here you might notice this is just equal to 1, because 0 factorial is 1, and then anything divided by itself is 1. Whoops, that 4 should be on the outside, right? Just like it was up here. So this is equal to 1. Maybe write yourself a little note, this fraction equals 1 or something, however you want to write it. And then 2y quantity to the 4th, that's 2, 4, 8, 16, yeah? Okay, and then 4 factorial over 3 factorial. Well, this is 4 times 3 times 2 times 1, right? And this is 3 times 2 times 1. So isn't it all going to cancel except for the 4? 4 times 3 times 2 times 1 divided by 3 times 2 times 1. Write that out if you need to. Rewind me like 10 seconds and write out what I just said. It's going to be 4 times 2y to the 3rd, so 2, 4, 8, times negative 3. Okay, this one I'll do over here. 4 factorial over 2 factorial, 2 factorial. That can cancel. I can reduce that, and I end up with 6. Oh, I did it again, didn't I? Sorry about that, guys. I end up with 6. And then 2y quantity squared, and then negative 3 squared. We already did this one over here. Same exact fraction. So that's 4 times 2y times negative 27. And we already did this fraction over here. That's equal to 1. So that's going to be plus, what is that? 3, 9. So 9 times 9, 81. And we're in the home stretch. These problems are not short. 16y to the 4th. What is this? 32 times 3. That's going to be what? 96. And it's a minus. Excuse me. Right? And then plus, what is this? 36 times 6. That's 180, 216. Oh, I don't feel like doing this in my head. This is going to hurt my head. I'm going to do 27 times 8. What is that? 56, 160, 216. That's minus. And there's that. Okay. You'll notice the alternating pattern with plus, minus, plus. That's going to happen when you've got the minus in between. Also, don't get so stuck in your ways and go, okay, this is a y to the 4th, right? 1, 2, 3, 4. 0, 1, 2, 3, 4. How come the coefficients don't match? It's not 1, 4, 6, 4, 1. Well, these are the coefficients before you start multiplying out the 2y to the 4th and the 2y to the 3rd and the negative 3 and so on. So you'll see this was equal to 1. Let me write it in a different color. This was equal to 1. This was equal to 4. This was equal to 6. This was equal to 4. And this was equal to 1. So that's where Pascal's triangle comes in. Those numbers don't stay the same if you've got other numbers going on in the problem. Okay? All right. If you have an expansion that's like a 6th power or a 7th higher powers, it's kind of annoying to have to write Pascal's triangle out very far. So that's why we have they're called combinations. 4 choose 0, 4 choose 1, 4 choose 2, etc. All right, so find the 6th term in the expansion of x plus 2 to the 9th. there's a lot of different ways to do this. I'm going to show you how I do it, and you can do it however you want. But what I think of is I want the 6th term, so I'm going to count to 6 on my fingers. And my mouth is going to say the power of x. So the first term has x to the 9th, x to the 8th, x to the 7th, x to the 6th, x to the 5th, x to the 4th. I'm going to write that down. And then I'm going to show you what I did one more time. Okay. I don't usually say it out loud, let alone all of the x's and stuff. So I need to know that the first term of the binomial starts with the highest power, which is 9. So I'm counting the number of terms, the first term, the second term, the third term, the fourth term, the fifth term, and the 6th term. Okay. I'm saying out loud the exponent on the x. So 9, 8, 7, 6, 5, 4. Okay. However you want to do that, I'm totally fine. That's just how I do it. Then I know that the 2, the second term, has to be to the 5th power because these have to add up to make that. So 4 plus what equals 9. And then I know the coefficients. It's 9 factorial, original, divided by exponents on the term, on the pieces of the term. And then I can go 9 times 8 times 7 times 6 times 5 factorial. And then 4 times 3 times 2 times 1 times 5 factorial. So a little math teacher trick, right? Math teacher trick again, 3 times 2. I could have done 4 times 2, but since those were together, it just was nicer to cross those out. And then reduce the 8 and the 4. So you're left with, what, 9 times 2 times 7 on top. So 18 times 7. That's what, 70 plus 56. Oh, my brain is not doing this for me right now. That's 126, right? Okay. I have a headache, a really bad headache, so excuse my lack of ability to do some basic arithmetic right now. So 126, x to the 4th times 2, 4, 8, 16, 32. 126 times 32, that's 4, 5, that's 2, that's what, 18 with that, that's 7. I should probably check this on a calculator considering how my head feels right now. 13, that's 10. That's 4. Actually, I have the answer right here. Let me just double check this. Yep, good. I can math. I can math. Hallelujah. All right. Okay, so that video was about 8 minutes longer than most of the videos have been. But there's just kind of a lot of explanation to do on that. So 12.5 is part of the test on, what day is it? Is the test on Thursday? The chapter 11 test. 12.5 is part of the test. I hope you guys are doing well, and I will see you on our call on Wednesday.